So welcome. My name is Wes Deason. I was originally a student here at Texas A&M University, graduated here in 2011, and I went to grad school out in Oregon and now work out at Idaho National Laboratory. This panel today, we have a great distinguished membership on our panel. I tried to gather students and professors and other researchers from within our field that have experience doing research as a student in the space nuclear research field. And for those of you students who are interested in doing this sort of research, hopefully they should be a good source for providing information about how you could get involved in the space nuclear community. And we're going to share our passions and a little bit about this. And so today a little bit about our agenda. I'm going to give a short introduction about the space nuclear community and just space nuclear in general. I want to talk about the sponsors for this panel, and I'll introduce our members. And then we're going to go through and talk one by one about our personal research experience in the space nuclear field. And then I have a few moderated questions that I have for our panel today. And then after that, we're going to open it up to you guys. If you have any questions or inspired to ask us, whether you want to know more information about the technology itself, if you want to ask specific questions about any specific fellowships that we mentioned during our talk, or have any questions about people in the space nuclear field that you would want to collaborate with and work based on concepts, just feel free to ask when we get to that. So to get started, I want to talk about our sponsor for the panel today. So our sponsor is the Idaho National Laboratory. So Idaho National Laboratory, it's located just outside of Idaho Falls, Idaho, and it's where I currently work. I work there under the Center for Space Nuclear Research, which I'll get to in a sec. Idaho National Laboratory is the Department of Energy's primary nuclear laboratory. They call themselves the National Nuclear Laboratory. They are home to, as you may have heard, the Advanced Test Reactor, and soon they'll be restarting the TREAT test reactor, which will function as a user facility. So yourself as students and your professors can come and use the facility that is available from the Department of Energy to do your research. The Idaho National Laboratory also does research in environmental science and homeland security. So if you have any interest in that background as well, you can go to our inl.gov webpage. We've recently revamped it to look all professional and millennial. So come check it out if you get the chance. We also are expanding into social networking. So come and check out our Facebook page, where there's a Facebook page for Idaho National Laboratory. Also, I want to mention our division within the American Nuclear Society, the Aerospace Nuclear Science and Technology Division. If you have the chance to become an official member of the American Nuclear Society, which I recommend all of you do, you have the option to join 2 professional societies. You have the option to join 2 divisions within ANS as a professional society. So the Aerospace Division is one of those, and we're very active. Every year we put on a space nuclear conference called the Nuclear and Emerging Technologies for Space Conference. And we'd love to have you come and join and learn and meet everyone who is involved with that. Pertaining to space nuclear research, the INL runs the device assembly facility that assembles the multi-mission radioisotope thermoelectric generator. It's currently the power source that's powering the Curiosity rover. So it uses a plutonium-238 heat source. And in a minute, I'll go into a little bit about radioisotope generators. In INL, also where I work, the Center for Space Nuclear Research is a small research group that is operated by the University Space Research Association for INL. And at the CSNR, we were founded and chartered as a center that would focus on space nuclear research, and we would do that through interaction with students. So one of our major programs is the summer fellowship program. Myself, Chris, Kelsa, and Vishal are all involved in that program. Dr. King has come as an advisor to that program as well. And where we have 15 to 20 students every summer come out and work on space nuclear projects at INL. And you get to collaborate and talk to all the researchers at INL, the researchers at the CSNR, such as myself and Vishal. And you get to really learn what it means to work on a project, work with a team of people that you've never met before, and come together and sort of work over a 10-week period to come up with a really cool space nuclear concept. We also offer a program for graduate students called the Next Degree Program. The Next Degree Program is a program that allows a grad student to come work at INL, where they can come and work on a project, actually an INL project, and you'll get paid 50% of your time. And during that time, you can use the work that you work on at INL towards your master's or PhD thesis. So if you're interested, come check it out. Send an email to us. You can find more information on our CSNR webpage. Just do a search on Google for the Center for Space Nuclear Research. And you can find information about our summer fellowship program, our next degree program, just about what the CSNR does. So I want to give a quick introduction about what is space nuclear, because some of you may have come to this today. Actually, Michelle, can we turn off the lights? Or turn them up on the panel? Yeah. So I'm going to give a quick introduction about what is space nuclear, because some of you may have come to this panel today wondering, what is that? I've never heard that before. I remember still my junior year as a student, and I learned there are such things as space nuclear applications in space. And being someone young and interested in space, it fascinated me. And so, according to my definition, I would say that space nuclear is the peaceful application of nuclear energy applied towards the exploration and colonization of outer space. So as nuclear engineers, we like to focus on the technology. And a lot of the technology that pertains to the research that we do as engineers in the space nuclear field can be divided up into what I think are 4 different sections. You have radioisotope power sources and radioisotope heating units that normally are used in low power applications. You have fission and fusion power sources. You have nuclear thermal propulsion, which is the use of a nuclear reactor to heat a propellant of some sort that operates similar to a chemical rocket engine. And lastly, you have your advanced propulsion concepts. So advanced propulsion concepts are concepts where antimatter propulsion is actually one of the more realistic concepts out there about what can be used for very far long-distance space travel. So all of these concepts can vary widely in the scale that they operate in. Specifically, fission and fusion power sources, you can have devices that are designed to operate in the hundreds of watts level up to the hundreds of megawatts level. The same with nuclear thermal propulsion. You see reactors designed to operate anywhere between 50 megawatts to even thousands of megawatts. Actually, the most powerful reactor ever to be operated at steady state, it was a nuclear thermal rocket tested out in Nevada in the 1960s, the Phoebus 2A. So now we're going to get into a little bit about introduction about each of our panel members today. I will start us off and talk a little bit about my experience, and then we'll go down the line here. So, like I said before, my name is Wesley Deason, and I was a student here at Texas A&M University when I learned about space nuclear power. I was absolutely fascinated by it, and I went to talk to one of my colleagues, and I found out that one of our professors at A&M actually did research in space nuclear power, and I went to talk to her, Dr. Shannon Braxton, and she referred me to our CSNR summer fellowship program. So I looked into it, applied, and that was my first summer. I came there not knowing hardly anything, just finishing my junior year at A&M, and went there and started working on a project where we had to do a nuclear reactor design. and it was an absolute wonderful experience just to getting to work on it, and it completely expanded my horizons. When I came back to A&M, I decided I wanted to take the orbital mechanics class offered by the aerospace engineering department, and that was crazy. Probably wasn't the wisest choice given it was the first semester of my senior year at A&M, but I made it through it. The professor, I'm not sure if it was a pity pass but he worked with me, and I learned some really great things and actually got to apply it. I applied again for the fellowship program at CSNR and was able to go there, and actually got to apply some of the stuff I learned in my orbital mechanics class the next summer at the CSNR. After that, I went on to grad school, and after finishing my grad school program, I managed to get a job working at the CSNR and actually working on a specific nuclear thermal rocket project, and that's what I work on now. So one of the things we work on is looking at a nuclear thermal rocket, but seeing what alternative design methods we can apply to that. Whether we need high enriched uranium, or we want to switch to low enriched uranium, or we want to look at a type of tungsten fuel or graphite fuel. There's so many different design choices, and you really have a different design condition that you design to in space nuclear. So now I'll pass it off to Vishal if he wants to talk about his experience.
Sure. So like Wes said, my name is Vishal Patel. I go to school here at A&M as a graduate student, and I am a researcher on the next degree program at the Center for Space Nuclear Research, and right now I'm working on TREAT Restart, which isn't a nuclear thermal rocket, but I do that on the side as I can. But for the last 6 months or so, I was working on the team doing that. But I'd like to kind of explain how I kind of got here, because I'd say I was a naysayer for space nuclear research about 2 or 3 years ago. I kind of had the idea, I didn't really know much, and I had the idea of, oh, there's not really anyone doing research in this field, there's not money in it, so even though it looks cool, like it's not a good pathway to getting a job one day. And so I'll start you with that and show you how I got to where I'm here now. So I got my master's here doing a small modular reactor design. And so I was kind of looking for a PhD topic and looking around, and I found the Center for Space Nuclear Research had an internship program, and I said, hey, I'm not doing anything this summer yet because I couldn't find an internship at the time. So I applied there and I got it. And the first summer there, which was two summers ago, I worked on I'd say kind of a out there project. We took a kind of a spherical reactor core and with really kind of out there materials, and heated it up to about 3,000 degrees Kelvin on the outer edge to let that just kind of like a light bulb black body radiate outwards onto a mirror and onto PV panels to make electricity to run electric propulsion. And that was our project, and that was kind of really out there, and that really kind of almost turned me off from the space community, because I said, this is really, really fun. It was a nuclear reactor design that no one ever really has looked at, so it was really cool, kind of 10-week opportunity, but no one's gonna, take that and say, oh, hey, let's go build this. So for me, I wanted to go back and do SMR design for Earth-based reactors, trying to actually get those built. And at the time, it was still, I guess it was kind of at the peak, the SMR kind of revolution, and it was coming down. And so I was kind of thinking, hey, what's the kind of next reactor that there could be? And there really wasn't one out there that I knew about, except for, sorry, when I say next reactor, I mean kind of next generation, not necessarily water-based. And so I went to the the Space Nuclear Conference, NETS, in New Orleans in February of last year. And I met again with my boss at the CSNR, Dr. Steve Howe, and he proposed to me a SMR design for Earth-based reactors using nuclear thermal rocket fuels. I said, that sounds awesome. It kind of hits the coolness of space, but it's on Earth. And the idea there was that we could approach the development of a new fuel from two angles, one for Earth-based applications and one for kind of Mars-based applications, really. And that way you'd have 2 or 3 different funding sources that kind of have their hand in the game, so it could be a better way of actually developing the fuel. So I started doing that over the summer last year, and great experience. And then it sounds like a series of unfortunate events, which I think it was, but the CSNR got a contract to work on some multiphysics coupling for nuclear thermal rocket safety analysis, and I was asked to work on that kind of as a part-time job, and I said that sounds awesome. Multiphysics coupling is it's what it's about kind of in our field. You got to make sure that your neutronics and your thermal hydraulics and your structural mechanics are all in line together before you can actually kind of build a reactor. So that was a kind of a couple-month opportunity, and from that came a opening on the nuclear thermal rocket team at the CSNR, and by that time I was in it, and I wanted to see a nuclear rocket fly, so I joined the design team, and I did that for about 6 months, and so now I'm here. Oh, actually, another thing happened. Because of my involvement at the CSNR, I was able to get a position with the INL working on the transient test reactor restart. And if you're unfamiliar with that, essentially it's a reactor that we had in the 60s to the 90s. Essentially, you had this reactor to put fuel into to melt the fuel to find out what happens in accident conditions. And nowadays, I'm sure y'all have heard that there's the Light Water Sustainability Program and kind of next generation nuclear fuels, since they're coming out, we need a way to test them in accident scenarios, so TREAT's coming back online to do that, and I'm getting to work on that now because of my involvement with the CSNR. And yeah, so that's my kind of experience in the last few years.
So our next panel member is Dr. Jeffrey King.
Welcome. So I am a professor of nuclear engineering at the Colorado School of Mines. I'm still doing a little bit of space nuclear. I've managed to keep a student involved in space nuclear for the last 4 to 5 years. I started off a long time ago, actually. Well, relatively long. I came back. I got my, well, let's start at the beginning. So I got my degree in actually environmental engineering at the New Mexico Institute of Mining and Technology. And I decided that I wanted to work in radioactive waste management. And so I ended up at the Savannah River site. I was there for 4 years. I discovered in the process of being involved in radioactive waste management that I didn't really enjoy it. It's important, but I decided I really wanted to make waste rather than clean waste up. So I came back to school, and I was actually looking at, when I started coming back to school, I was actually looking at chemical engineering for my graduate program, and I interviewed at the University of New Mexico and ran into a man by the name of Mohammed El-Genk, who is not as involved these days, but at the time was sort of the leader, one of the 2 leaders in the universities in space nuclear power. And he was running an organization at the University of New Mexico called the Institute for Space Nuclear Power Studies. And he was very enthusiastic, and he's like, you want to make space power, you want to make, do nuclear in space, you want to do Amtex, you want to come work for me, and I will abuse you and make you work really hard, and you'll get a great degree. And it all sounded very exciting, and I kind of missed the I'll abuse you part. But it worked for him. And I ended up, he called me up. He's like, I'll give you money, and I've got this NASA program that you can come to school and do nuclear and do space. And I said, all right, that sounds a lot more exciting than chemical engineering. And so I bailed on the chemical engineering plan. And came to the University of New Mexico to do nuclear. And this was right in 1998, which, if you've paid any attention to things nuclear and things like the Department of Energy throws out this graph of student enrollment, and if you look at the bottom of that, that's 1998. Is when nuclear engineering died, and the bottom fell out of it. That's the year that the U.S. government stopped funding all nuclear engineering education. And so it was an interesting time, but it was space that drew me in. It was the lower space. So I did space research at ISNPS for 7 years. Got my master's and my PhD there, and then went off to teach. And I've been to two universities. I keep my foot in the door. I've helped with CSNR's program. I think the thing I'm most proud of, and the thing I'll close with on that, and I'm sure we'll talk about other things, but is if you get into space nuclear, and this is something that maybe the folks up here don't know. If you get into space nuclear, eventually if you start doing rocket design, you'll start using, you may or may not, probably will use the term spectral shift absorber. And it's one of the safety mechanisms that we use for nuclear rockets. So most nuclear rockets, or most rockets or space reactors, tend to be fast spectrum for various reasons. And one of the things about a fast spectrum reactor is that you have a lot of uranium in it, and if you drop it in the ocean, which is a significantly possible scenario since we launched from Cape Canaveral, and Cape Canaveral is surrounded by ocean, that if something goes wrong with the launch, it may drop in. And so when a space reactor goes into the water, you can have an increase in reactivity because you now flood the fast reactor with water, and the fast reactor becomes a lot more reactive because it went thermal and you have a lot of fuel. And so the spectral shift absorber concept is the idea of you put something that has a low cross section for fast spectrum, but a huge cross section for thermal, like gadolinium or europium, or some others, boron. You put it in the reactor so that you keep the reactor from going critical when it goes in the water. And I won't claim to have invented that concept because actually if you do the research all the way back into the 60s and the SNAP programs in the 60s, they'd figured this out. I will, however, say that we were sitting around one day and we needed a snappy acronym because we were, absorbers that you put in the reactor to keep it from going from fast to thermal and whatever, that was too long. And we were writing papers and we needed a snappy acronym. So we actually coined the term spectral shift absorber. And so it's kind of a neat, and SSA, and that was a nice little, and so it's kind of a neat thing whenever I read a paper or I go to a talk and I hear people talking about SSAs, and I'm like, I coined that term. And people are still using it, years later, and it's actually becoming more common. And so the point there is that as a graduate student in space power, you do have the opportunity to leave a tiny little legacy out there that may get used later. So that's my achievement for space nuclear.
Thank you, Dr. King. Next, we're going to have Chris Morrison.
So my background is actually aerospace engineering. I grew up in Albuquerque, New Mexico. And right at the time I was growing up, there was something called the New Mexico Spaceport, or Spaceport America. And they were going to do space tourism and launch people into space. And that got me excited about space. I said, we've been stuck on Earth for such a long time. I want to work on getting off Earth. I want to go to Mars. I want to go into the solar system. So looking around at the time, I thought rockets, were the place to go. So I went to a place called Embry-Riddle, which is in Arizona. There's also one in Florida, but I went to the one in Arizona. And learned as much as I could about aerospace engineering. What's the future of space? What's the future of space flight? And come around my junior year, I kind of was looking around and I said, what am I going to do exactly? Am I going to work on rockets? Am I going to do tourism? And at the time, I had a really great professor, Dr. Fabian, who taught a class called Exotic Propulsion. So I took his class because I was interested in what the future is. But at the time, I kind of thought, all this stuff is way out there, crazy. But we went over the history and the uses and the, everything from kind of antimatter wormholes. But I kind of latched onto the more immediate things. And specifically, I kind of looked around. Originally, I saw a lot of electric propulsion. And I said, hey, electric propulsion is awesome. It makes it to where your rocket, instead of dropping stages and needing to be large, can be very small. It could be like a car. You fly around the solar system and you just fill up the gas tank. So I began to look in there, and I thought I might go to grad school in that area. But a little bit later in the class, I did some research, and the key thing there was that it's a great engine. There's lots of engines out there, but there's no power. There's no power source for them. So they're useless unless you have that. And I was looking around at grad schools and I said, who's doing this? Where's the research? Looking all over every website, every professor that I could find. And all I could really find was there was something called the NETS conference, which was the Nuclear and Emerging Technology for Space Conference. So I ended up not going to that year, but when I applied to a bunch of grad schools, there was a school up in New York that had a combined mechanical and nuclear and aerospace program, which I thought, oh, maybe there's some synergy. Maybe they're working together on some space reactor. And I get there, and there's no one combining. There's nothing, no synergy. But I did meet a nuclear professor who was actually a great resource to me, because most research advisors you get there, they already have their project planned out for you. They say, you're going to work on my research and you're going to work in this area. But this professor agreed to let me work on space reactors. And since I had gotten kind of a full teaching assistantship if I needed it from the school, I had the ability to do that. So I went there and started, thinking, okay, I didn't know anything about nuclear at the time. I kind of knew that it was great. It was a power source. We had reactors on the ground. How do you adapt it for space? And it seemed like we could do it in the short term. So I began to do research, and I talked to you about the propulsion aspect. So you can use nuclear energy either for electric propulsion, or there's a lot of research that's been done into what we call thermal propulsion, where you use the reactor as a heat source to expand a gas, just like a traditional chemical rocket, but you can get much better efficiencies and much lighter rockets, or at least much less propellant, so you can carry more with you. So, and then I looked around, and the other use other than propulsion was electric generation. So if we send someone to Mars or to the moon, we're going to need electric power. We can't keep someone alive without electricity. When the astronauts went to the moon, they had what was called a RTG, which was basically something that you could think of like almost a waste product. It was the leftover of, they couldn't use this in a plutonium bomb. So it was an isotope of plutonium that's left over, and it generated a lot of heat. And they said, what are we going to do with this? And they said, oh, let's put it in space and make thermoelectric generators. And now there's things that have flown into the outer reaches of the solar system, the Voyager probes that have been operating for like 40 years just on this power source. And that's something you could never have without kind of a nuclear background. And then as you go up in power, you need to start using fission, because fission is a lot more, you get on-demand power. So you can use as much as you want. So say on the moon, we go to the moon, you think, oh, there's lots of sunlight there. Maybe we can use solar. But the fact is the moon has 15 days of darkness and 15 days of light. So unless you carry 15 days worth of batteries with you, you can't make it work. You need nuclear to go anywhere beyond low Earth orbit. So I got excited and did a lot of reading. There's a lot of good books that have been written. They're hard to find, but there's a lot of people in this field that are passionate and have written materials. So I'm a third-year grad student now, so for the last few years I've been basically reading everything I could and learning nuclear engineering, because at the time when I first started I didn't know what reactivity was. I was like, what's reactivity? But I'm now to the point where last summer I actually spent the summer at CSNR, which Vishal and Wes talked to you about. And that was a great opportunity, because that's a community where as a student you can come in and get up to speed on what exists and do the analysis and really get excited about the field. So if you're thinking about this field, apply to the CSNR. They usually like more seniors or generally grad students because it's highly competitive, but if you show your passion and whatnot, there'll be opportunities even if you don't get accepted to that, because the community here is very friendly. The people in this area, there's not, as we said, a lot of research money, but there's a lot of very good people that will spend time and effort because they're passionate about this subject. It's not about really making a lot of money. It's about changing the world, or changing the solar system, really, if you look at it that way. So I'm in my third year, and I'm doing research into basically electric power generation using nuclear power, and I've kind of focused more on what I would call a Brayton cycle. On the Brayton cycle, and I've made some decisions on, that one's kind of, I could talk to you all about my research, but I think it's more of an introduction. But I'm excited for the future because I see, I said, I started looking at rockets, when I first started, and rockets are great, but what I decided was they're being solved right now. Before 2000, the cost to go to space was about half your weight in gold, and that was just for you. If you had to carry your life support equipment and everything else, it was impossible. And if you wanted to launch a reactor in space, it's basically going to cost, just to launch it, half its weight in gold, and then all the engineering and development. But in recent years, there's a company that's driving innovation that's called SpaceX, and they've dropped the price of spaceflight by about a factor of 10 and are trying to drop it more like a factor of 20. So the cost to get to space has really been one of the biggest barriers to the space nuclear fuel. It was just too expensive to do this stuff, too expensive to go to Mars. But in the future, that door is opening. So there's an opportunity here for a lot of people in the future. You're kind of making a bet. You're making a bet that you're saying, hey, I think that this will come through. I think that there's going to be people working in this area. But it's a good bet, in my opinion. I think in the future, right now there's not a lot of money in it, but in the future that could really change. Space nuclear is kind of like a sinusoid. There's always a project, and usually it's been canceled, but now it's gotten to the point to where a small private company can do this. So it's gotten cheaper, and that's a key thing that we need for the future. So I'm excited about the future, and hopefully I can get you excited about it too.
Thank you, Chris. Our next panel member is Kelsey Beninsky.
All right, hello everyone. My name is Kelsa. I'm a recent graduate from Penn State. I graduated in December with degrees in mechanical and nuclear engineering. Currently, I started in January. I'm a grad student at the University of Tennessee in Knoxville, and I'm pursuing my PhD in nuclear engineering. Well, my research background is in nuclear thermal propulsion, similar to Vishal and Wes, I believe. I started my research experiences as an undergrad, actually, and I'm going to sort of echo something you've heard from other panelists. I started getting involved after going to Nuclear and Emerging Technologies for Space Conference. So if you're really interested in nuclear space, I highly recommend it. I paid to go to the conference myself, my first time going, and it was definitely worth more than I paid. And we have a really small community, but everyone is really friendly and really wants to help students because you guys are the future, and I think we all want to get you excited about the future as well. I started my research after that conference. I received funding to do a research project at Penn State, and I sort of got to bounce ideas off with people I met at the conference, and I was able to do an independent research project, sort of characterizing the tested nuclear thermal propulsion fuel forms that have been tested in the United States and former Soviet Union. And I think based off that work, I was able to get a presentation at the next NETS conference, and I was able to hand off some of my work to CSNRs if it could be of use to them. So that was a really cool experience to do as an undergrad. I was a sophomore, so if you are able to have an advisor that's supportive, you can definitely have some opportunities to do at your local university. If you're not able to secure a summer internship. After presenting at NETS, I was approached by NASA, and I was a NASA intern last summer. And do you mind if I make a pitch about being a NASA intern to them? Sweet.
It's your experience.
Yeah, I'd love to talk to you guys. What I did at NASA was I did work doing nuclear thermal propulsion, mechanical component design. So I'm really thankful for my mechanical engineering degree too at Penn State. That really helped me this summer. So I was in a special program at NASA. NASA has, you can be an intern at NASA over the summer. There are co-op opportunities at NASA where you can work in nuclear space, whether you like space radiation, if you like doing that sort of analysis. There's nuclear thermal propulsion work. There's nuclear electric propulsion work. I'm not going to say there are lots of opportunities, but they are available. And typically I see nuclear engineering is not the most representative field in these areas of research at NASA. So it'd be nice to get more nuclear engineering students involved if you're interested. I was in a special program. I was in NASA's Propulsion Academy. I think it's not as well known. I had never heard of the Propulsion Academy. I'd applied for internships at NASA through their site OSSI. But the Propulsion Academy is really cool. And our principal investigator, Dr. Omar Morales, he was a Academy alum. So he's really interested in making sure that nuclear space is represented in the academies. My experience in the Propulsion Academy, basically what you do is you work 410s during your week, and after you work your 410, you have little classes that you go to, and they teach you about all different types of propulsion. So I was not an aerospace student like Chris, but I got to see what's the difference between solid, chemical, composite, nuclear propulsion, and sort of get a background. So I think that's pretty cool and an advantage if you're a nuclear engineering student. You get to learn about that sort of stuff without having to take a formal class. But you might say, 410s, that's great. Now I have a great 3-day weekend. Well, in this program, you don't. Instead, the last 3 days of your weekend, you work again, but this time it's cooler, I think, than working the 410s because you get to, NASA will fly you all over the country, and you get to network these last 3 days. Let's see. So during my program, we got to see a bunch of different NASA centers. We saw Kennedy. We saw Marshall was where I was based out of. There are other academies that might be based out of other places. We got to see NASA Glenn. Previously, they went to NASA Stennis. That's where they do all their chemical rocket testing. And we also got to see Plumbrook, which is a testing facility that was actually designed originally to test nuclear thermal rockets. So that was super cool. And then we also got to go to Joint Propulsion Conference. So that's another great networking opportunity if you see you're in the Propulsion Academy and now you're like, what's all the other space stuff out there? I'm interested in whatever. Now you get to network with other professionals in the aerospace side. And we also got to see cool commercial space ventures. So we got to see SpaceX and Virgin Galactic. So it was basically, I think, a priceless opportunity, and it's not well known. So I wanted to make you guys aware of it. My specific project, we did nuclear thermal rocket component design, and it was a lot of fun. There were 3 of us on the project. We got really close because we had to spend all our time together. But I got to do some studies to experimentally determine what's the best way to make our neutron moderator in the nuclear thermal rocket. And we set up an experimental test, subscale flow test rig, and it was a lot of fun. So we got to make an actual contribution to NASA's efforts making a nuclear thermal rocket one of their pathways that they're pursuing. And I strongly recommend the Propulsion Academy. It was a great opportunity. It's really going to set you apart if you decide either to get a job and you have that, it looks good on your resume, or if you want to go for fellowships, specifically NASA fellowships, I think that would really help you too. So that's sort of my research background.
Thank you, Kelsa. And now we have Bill Lyon.
Yep. Hi, everyone. It's very interesting sitting up here and listening to everyone's work and realizing that I'm kind of the old man on the panel here. So that's also a new position for me, actually. So I've always kind of thought of myself, hey, here's the young guy doing this stuff. But time passes and things change. And so it's really fantastic to me to see a younger group of people, and especially the students that are on the panel as well, graduate students, and the people that are here in the audience that are interested in this topic. Because one thing I will echo, as everyone here kind of tells you and has told you in their brief outline of their work, is that there's something about space nuclear applications that drives people's passion. It makes it's a very interesting subject. It's kind of esoteric, but it is very interesting. And if you get the bug, you kind of keep the bug forever, it seems like. So I'll go back a little bit in time here on my involvement in space nuclear work. Started when I was an undergraduate student at Texas A&M in nuclear engineering. One of our professors got our department involved in what at the time was almost purely an aerospace engineering program. It was sponsored by the University Space Research Association. Our aerospace engineering department here was part of I think it was the founding year, actually, that I became involved in this project, 1985. Ancient history for most of you. maybe 84 is when it actually started. And it turns out that my professor, Dr. Petticord here, who is now the head of the Nuclear Power Institute here at A&M, knew the department head at the Aerospace Engineering Department, also the dean of the College of Engineering, and said, you know, we really need to get our nuclear engineering department involved in this program. And at first there was some resistance to that because there were only 4 slots for students to be involved in this, and the program as it was envisioned was to be a collaborative participation of multiple universities, and each university was going to send 4 students to work together, and then in the summer program, the summer aspect of that, we were all going to go to a NASA center, continue that work, and then present all of that work at a large conference at Kennedy Space Center at the end of the summer. And so there were only 4 slots per university, and so we somehow wrangled a single spot for a nuclear engineering student to go with the aerospace group, and I was fortunately chosen to be the nuclear engineering student that got to go in on that project. And when we started this project, the idea was to develop, you know, innovative applications in space. Didn't have anything to do with nuclear applications, in fact, but we kind of shoehorned ourselves into this. So I met with the aerospace engineering team. We started talking about what we were going to do. The plan was a manned Mars mission. And so they were looking at all kinds of stuff, and their background was all in aerospace engineering, chemical rockets, and I said, and I went up to talk to the guy who was doing the orbital mechanics work in our group, and I said, you know, a nuclear thermal rocket has an ISP of like 3 times what you're looking at for your chemical system. We could get there a lot faster if we did something like that. And he goes, well, what's a nuclear thermal rocket? And I said, well, let me talk to you. So I spent the next week talking to him about the NERVA program and the tests that were done in the 60s of development. I showed him film of rocket tests and said, here are the characteristics of this engine. And he's like, wow, we could really do some amazing things with that engine. So he revamped his whole orbital mechanics program and started putting in the data for this nuclear thermal rocket. And I also started talking to the other guys on the team that were looking at, okay, transportation systems, on-site power systems. So it turned out, apparently, I'm quite a persuasive speaker because I had us using a nuclear thermal rocket to get our people to Mars. I had us using a nuclear engine to power a cargo spacecraft using electric propulsion to get all our stuff on orbit. And then I had us deorbiting a nuclear reactor to put it on the surface so that we could survive while we were there. And I actually came up with another idea. I said, well, if you don't want to deorbit the reactor, let's put this spacecraft into I don't know what the equivalent term for geosynchronous orbit on Mars would be because it's not geo, but into a synchronous orbit and beam down the power to our site so that, you know, we have power on the surface. So I was able to fully integrate nuclear technology into every aspect of our mission. And in fact, we created this, what we called a split sprint mission scenario, whereby we would load up everything on a large vehicle built on orbit, send it to Mars using nuclear electric propulsion. Of course, it has to spiral out from Earth's orbit because nuclear electric propulsion is characterized by very high efficiency but very low thrust. So you can get things, very heavy things, a long way off very efficiently, but it takes a long time to get there. Well, you don't need astronauts sitting on there spiraling out from Earth orbit. So the idea was you build a cargo vessel, send it off. A couple of years later, after it's just about on its way to Mars and establishes a Martian orbit, you send a manned spacecraft out using nuclear thermal propulsion. You get those guys there. In fact, the transfer we used was about 6 months if you do it the right way. You can get there very quickly, get to Mars very quickly, and then you made up on orbit. So we coined this idea of this split sprint mission scenario. In fact, the people at NASA, when we were involved in this at Johnson Space Center, where we finished it up, were very intrigued with this idea, and they had us write up a NASA technical note on this kind of scenario that they told us that nobody had ever come up with this idea before. So that was a very interesting thing for us to do that. So it was a very exciting program. We got to go present this stuff as I said, at this conference at Kennedy Space Center. Well, when we got together, there were many universities that were involved. MIT, I think Penn State, Michigan. I think there were about 8 universities that were involved initially. And when we presented things at this conference, and again, this was very interesting. We were the only ones who used nuclear technology in our presentations. And everybody kind of looked at our research after it was presented. It's like, wow, that's very interesting. So that program ended. We all go back to school. The next year, they repeated the program, and I was not involved directly in the development, but I was kind of as an advisor to the nuclear engineering group that was now involved. We were kind of embedded in this project at the time. It's very interesting. In fact, we had a representative from USRA come up into the nuclear engineering department, teach a class on propulsion to get nuclear engineering students interested in space. And it was a very interesting class because, again, kind of like what you were involved in, is you get to see a bunch of things that nuclear engineering students never get to see because you're focused on your curriculum and what you're studying. And so it was very enriching in that sense. So the next year, I go to this conference at KSC, and now, amazingly enough, every single presentation is using nuclear thermal rockets, nuclear electrical propulsion, nuclear power plant, because they see the effectiveness of this technology, the potential for that technology. Our presentation, when we presented what we could do, getting people to Mars, getting them there and the speed we could get them there, having the power on site when we got there to do amazing things. Everybody looked at that as a very revolutionary concept, and it is a revolutionary concept. Certainly there are some barriers. As we mentioned, nuclear research, nuclear testing, flying reactors in space, it's very expensive. There are a lot of considerations you have to take into account. Accident scenarios, environmental protection, technology development, high temperature materials. There are many, many areas. Now those are all challenges, but what they also represent is opportunities for people like you to get involved and solve those problems, to find innovative solutions and find innovative ways to get those things and make them happen. So let me fast forward a little bit. So that was my introduction to it. I got a chance to go to Marshall Space Flight Center to meet with, in fact, Steve Howe was one of the guys that I met at this meeting. He was there. There was a whole Man-Mars mission meeting, and I was in on the ground floor of kind of that activity, which was very interesting at the time. Johnson Space Center was an amazing opportunity as well. Kennedy, to meet all these other groups. And so, again, it was kind of an exciting time in that respect. When I got back to A&M outside of this program, I tried to continue my emphasis on this area, and I was able to successfully kind of negotiate continuing activity in this. And I talked to one of my professors. He knew some people, and I wrangled an exchange program at the University of Stuttgart. And now it seems kind of out in left field, but the University of Stuttgart has a very interesting institute there. It's the Institute for Raumfahrtsysteme, and that's Institute for Spaceflight Systems. And they were doing research at the time in developing plasma rocket systems. And they were actually building these things in their lab and running them. And it was primarily funded, amazingly enough, by the U.S. Air Force. But they had a very advanced astronautics lab there, and they were building these things. And so for me, it was a very interesting opportunity. So I went over there. We worked out a deal so that I could go work for them. And so again, I'm there working with a group that's developing a very fundamental technology. And what I was doing with that for my project work was taking the fundamental data, real experimental data that they had on these systems, and marrying that to nuclear power systems. As we mentioned earlier, these plasma rockets and other systems, there's ion drive systems, there's all kinds of interesting technology out there. But without the appropriate power source, they're not really going very far. And to carry large payloads, to move things long distances, you need a power source like a nuclear reactor. And so my whole focus on that project was to develop, using their data and my modeling expertise and knowledge of nuclear systems, to build a nuclear electric propulsion conceptual vehicle based on that information. So I developed that. I designed a piece of software that analyzed it, and it was designed for low Earth orbit transfers. So if we had to move large cargoes from some orbit to another using nuclear electric propulsion, this software would analyze that. It would optimize the transfer. I built my own orbital mechanics model to allow us to optimize whether you wanted to get there in the shortest amount of time, or you wanted to carry the most amount of payload, or you wanted to minimize propellant. All those things were potential. And I ended up making that my master's thesis. And so it was a very interesting project for me. As part of that work, we were doing some activities at A&M with Westinghouse Hanford Company. At the time, they were looking at testing nuclear fuels for potential space applications, and they were involved in a program that was sponsored by both NASA, the Department of Defense, and the Department of Energy, called SP-100. SP-100 was a space nuclear power system that was designed to deliver 100 kilowatts electric on orbit for any potential mission that you wanted. DoD had their interest in a high power system for low Earth orbit applications. NASA had an interest in power system of this kind for on orbit and interplanetary space missions. And so I got involved in that program through A&M and ended up, instead of pursuing a PhD, which I was planning on doing, the guys at Hanford offered me a job and said, hey, we know that you're able to do this work. You're already doing some work for us. Come up here, work on the space nuclear work for us, and have a good time. And I'm like, okay, I think I will do that. And so what was really interesting about this program to me was it wasn't just conceptual. These guys were building fuel rods. We were fabricating them in-house. We were taking those and encapsulating those, putting them in reactor and analyzing the performance of these as they were irradiated. And so my function on that project was to design the capsules that we put these fuel rods into. So we were doing this active testing program. And then we would pull the samples out of the reactor. We would do the PIE in-house, and we did the evaluations on the fuel. And it was an amazing opportunity, again, to do some things with exotic materials. We were using uranium nitride fuel. We were using niobium-based cladding materials. It was a liquid lithium-cooled reactor, so we were encapsulating all these things in liquid lithium. It was a very exotic and very interesting project because it wasn't a standard type of irradiation analysis. We did this work in the fast flux test facility, which was a liquid metal reactor at Hanford, very large. In fact, the largest one I think ever built in the United States. It operated for about 10 years. It was an amazingly efficient system. In 10 years of operation, it never had a single failed fuel rod, not one. And we extended burn up well over 100 gigawatt days per ton in these systems. We used mixed oxide, plutonium, metal fuels, uranium nitrides, carbides, pelletized fuels, all kinds of different things in this reactor. So again, it was an amazing opportunity to learn about some very interesting and exotic things and to do real hands-on work in design and analysis and post-irradiation examination. So I worked in that group for many, many years, and until, unfortunately, the program kind of dropped down. As I mentioned before, one of the other characteristics of nuclear space applications is the funding levels are very cyclic. And funding is really driven by two things. There has to be an interest by some organization. So in that sense, it's really tough because it's a chicken and egg type of situation, right? You have NASA says, we have a need for a deep space mission. All right, so the rule of thumb, and we mentioned it a little bit earlier about RTGs, is that if you're going to go anywhere beyond Earth orbit, say to Mars, anything beyond Mars, at Mars or beyond, solar intensity is just not enough to power a substantial spacecraft, right? Because you know that solar intensity drops off as 1 over r squared, right? So it changes very rapidly the farther you get away. Once you get to Mars and beyond, you'd have to build solar panels that are the size of this building in order to get, the power that you need for some of these larger spacecraft. And they gave some good examples of why all our deep space probes, Voyager, Pioneer, the mission now that is going to Pluto, I forget the name of it. New Horizons. Every single one of them is nuclear powered. They use RTGs, what I kind of term a nuclear battery, because that's what it is. It just sits there and it pumps out electricity for a decade or more. Solid state, no moving parts. It's very efficient, very effective in that sense. So all of these spacecraft need nuclear power. The Curiosity rover that's on Mars right now is a nuclear powered spacecraft. In fact, it's the most powerful one ever built. So there are opportunities, real world opportunities for that kind of thing. The key is that there needs to be a solid mission from NASA. NASA or somebody else has to drive that technology. And here's the chicken and the egg thing that I mentioned before. If NASA says they have a mission, they're like, well, we're not going to pencil in a real world mission something that the technology doesn't exist, because we don't want to go on a 10-year project to develop the technology. We want something that's kind of available now. On the other side of it, the Department of Energy or other research organizations are saying, like, well, we're not going to fund the development of a technology unless there's a mission. And so what you see, the cyclic nature of these programs, is that a mission evolves, and as that mission evolves, the funding comes from other sources within to join up with that and made up with that mission to provide the technology. The technology development window, though, is typically so long that the mission initiative kind of either happens or goes away before the technology is developed. And then, of course, as that drops, so does the funding for developing. Because without the mission, there is no technology development. There's no need for that, right? So what you have is you kind of drop down to this ground level base of funding, kind of like the situation we're in now. And so as all of us have seen, these projects go up and down and up. SP 100 was a multi-million-dollar project, multiple agencies, General Electric was the primary contractor on this thing, and this is a big deal. This is a big deal. It was working at multiple positions in the United States. Not only were we doing testing and development of the fuel form at Hanford, we were also modifying a reactor building that was across the parking lot from where I worked, gutting the entire thing because the plan was to take an entire prototype SP 100, fully built, and put it in that building and full upscale test it, the whole entire thing. Nuclear reactor, thermoelectric generators, radiator systems, cooling systems, everything, just as if it was in space. And to evacuate that entire building, put it in a vacuum, and run a full up test of this thing. We were spending $2 or $3 million a year just to get that facility ready for that. And so, again, that points to the idea that, you know, if you're going to do this, it's a big time thing. And if you're not, it's very hard to sustain that level of funding. And so many years, if you look back in time, and when I first started getting involved in this, it was kind of the same thing. We would see that there was a big emphasis in the 1960s and 70s on nuclear thermal rockets. Well, in the early 70s, the administration decided that we weren't going to go beyond the moon, and so the mission disappeared, and so nuclear thermal rocket research trailed off and disappeared as well. Later, in the 1980s, there came this idea that, hey, we're going to need a lot of power in space because of this thing called the Space Defense Initiative, SDI. Cold War was ramping up at the time. NASA had a mission. DOE supplied the technology development for that mission. The mission went away. So did the funding for the technology development. So one of the things to keep in mind is that these programs are cyclic, but the passion to develop that technology and the foundation that has been laid by prior research in these areas is still there. All that information is still there. There are passionate people that are still involved. And so, again, if you're willing to fight the good fight, in that sense, if you get the bug and the passion for doing this, it can be a very interesting avenue for your career. And so, for me, it's been very interesting. I haven't been involved in this in quite some time. I've kept my eye on it. I've tried to see where I can get back involved. I would love to. And so one of these days, another mission is going to come along and people are going to be needed. And, you know, we are those people. So I guess that's my total message there, right? And I probably talked way too much, so I'll let us move on to some other things. But that's my background and history in this program. So
Thank you, Mr. Lyon.
That's okay.
Professional engineer Lyon.
There you go. There you go.
So I have a few moderated questions I'm going to ask our panel here. And during this time, think about questions that you'd like to ask us. If there's something that I miss here, some of our panelists miss. We'll just wait for the questions from the audience. So I'm going to start out with my first question for our panel is, how has your research in the space nuclear field impacted your research in other fields of interest, so nuclear and non-nuclear? So whoever wants to start can.
Who wants to start?
I'll start. Okay. Well, first and foremost, my research motivated me to get my PhD. I think doing research, especially in this field, I got excited about doing research, and I was like, yeah, I guess I could do this a little bit longer, the school stuff. So I'm trying to specialize in nuclear materials right now. And that also stemmed from my research. I really found, especially with nuclear thermal propulsion, we're operating at such high power levels in such extreme conditions, sort of similar to our Gen 4 reactors. And I thought, wow, the mechanical design and the neutronic analysis, while that's non-trivial, it can be done in the current state of the art, but we're really limited by the materials and their operating limits. So if I really want to make a contribution that's going to help us on Earth and then finally get off the Earth, I want to go into looking at this material design, specifically with an emphasis in nuclear interactions with the materials. So it has impacted me. I don't plan on just staying in nuclear space. I think I was told by some of my mentors, you need to find something that you can do all the time, not just space is cyclic. Again, So what are you going to do to sort of make that average at the top of the cycle? So I think I could do that with nuclear materials.
Yeah. So my PhD research is actually looking at fuel forms. So in space, everything is dominated by high temperatures. But when you look on terrestrial, generally we don't have high temperature reactors, and that's caused accidents such as Fukushima, where you have to remove this heat, and if the water boils away, then your reactor melts down. But if you implement new types of technologies that in space that are high temperature fuels, you could build Earth terrestrial reactors that would reduce a large number of accidents. So how I kind of see this as is that in space, the research that we do can really help the research on the ground. Because in space, it's a necessity. You have to do it. And then you take that technology and you can bring it back to Earth and say, hey, I have this new fuel form for LWRs that can, I'm looking at some things like small fuel particles and having what's called a very low thermal conductivity in those particles in a matrix and having a high Doppler feedback, things like that. So my research there's the SMR kind of research right now that's going on, and it follows a lot in the lines of SMR. And I think, so that's one area where it carries over. And then of course in the aerospace area, there's a chance that if people are serious about going to Mars, it's now gotten to the point where a government may not have to do it. It could be to the point where a smaller company could do it. So there's a lot of carryover with aerospace in my kind of area. So I see, there's a lot of opportunities. If you're the kind of person that you want kind of a fallback thing, nuclear is always a great place to go because there's always a need for nuclear people in different projects. And if you position yourself right, you can get into space nuclear when the funding's there. Or you could try to maybe fund it yourself or do research on the side. A lot of the people that I know are kind of hobbyists that do that. That, in their spare time, they do all these calculations, but they have a day job.
So NTR research has kind of sparked my interest in reactor dynamics. Essentially, to start up a nuclear thermal rocket, you have about 2 minutes or so to go from 0 power to full power, which is like between 400 and 700 megawatts thermal. And so you have a really fast kind of controlled kind of approach to reactivity, which you don't really have time to do your 1/m curves and wait for things to come to equilibrium to measure how much reactivity you have. And so that idea is a really cool kind of thing that's, I'd say it's been solved because they've been able to turn these reactors on before in the 60s in testing phases. But I think these days we'd have to show it on a computer first before we could actually just go out and do it. So that's one of the big things that I'm looking into now. And now it's working for TREAT, which is, literally you pull a rod out and see what happens. And so a lot of the same dynamics and physics go into modeling that reactor that would be going into NTRs.
So I'll talk a little bit about my experience about how space nuclear research has formed my viewpoint of other nuclear research that I've done. One of the impacts that it's had is helping me consider my project as a holistic design. And when I mean that, I mean how many ways does the work that you're doing as a nuclear engineer connect with fields outside of your own, and how big of a box do you draw around the work that you do? One of the first things you learn as an engineer is you draw the box around your design and you say, okay, this is my box and this is my free body diagram and here are my forces that are being applied onto this object. And then you calculate the solution to your problem based on those forces. I think space nuclear research has impacted my viewpoint on the research that I do by teaching me that many times there are factors that impact your design that are far beyond just what you immediately think are the factors. So whenever you're doing a reactor design, it's not just putting together a critical mass of material and saying, hey, I have a reactor, this is great. There's so many other factors, and in fact, you may learn that neutronics is not the first factor that you look at when designing a reactor. It may be the fourth or fifth factor that you actually consider whenever you start really getting into the design and start digging into it and start iterating between your different design conditions. You start learning that as a nuclear engineer, you have to be a part-time politician, a businessman. You've got to learn the work that you do. You have to be able to communicate what you're working on, and you have to consider that as part of your equation that you're computing, on paper. And so that's probably one of the things that I learned in the space nuclear field.
Do you have something you want to add?
Yeah, I think the interesting thing that I find is that technologies, there's a flow back and forth in certain technologies, and that one that I like to mention where we're doing reactor design projects, particularly the reactor design class I run, is well, why do y'all think about heat pipes? And the usual student response is, heat pipes? And I say, yeah, heat pipes. There's this technology that NASA came up with during the nuclear rocket days, or during the nuclear power days, that you can conduct heat through a pipe several tens to hundreds of times more efficiently than if it was just a solid pipe. And there's no moving parts, and it works, and there's one on your laptop. And then that usually spawns off an evolution of going and looking at new things. On the other hand, it's also kind of interesting to see where technologies are flowing back, in that right now we're looking at, when we look at some of the kilopower nuclear energy sources, we're starting to talk about the uranium molybdenum fuels, which are, were primarily studied for the reduced enrichment for research and test reactors program. So it's kind of interesting to see research that I'm in a different area come back the other way.
Yeah. Yeah. Normally with the space nuclear, you're beyond the realm of technology, but yeah,
it's kind of,
it's one interesting one.
Yeah, I think for me the cross-cutting aspect is that space nuclear applications, as we've all kind of discussed, kind of usually push well beyond the operational parameters that we would consider under normal terrestrial reactor conditions, commercial reactors, et cetera. But what it does do is as Wesley mentioned, it kind of lets you know that there's actually a domain out there that's beyond where you normally think. And I think one of the key things that we try to get across to people all the time, especially students that are learning something, is that oftentimes we will constrain ourselves in our thinking based on a box that someone else has kind of placed around us. There are all kinds of interesting applications and crossover applications, I think, in space nuclear applications with Gen 4 designs. There's liquid to metal reactors, there are high temperature reactors, other things. And so materials aspects that I learned being involved in the space nuclear activities I was actually served me quite well in proposing and thinking about and considering those aspects in more innovative reactor designs. And so I think the experience I gained in working with liquid metal reactors and actually, designing capsules and testing fuels for that environment was invaluable, because you don't get that research very many places. And so to me, again, when somebody talks about an LMR, talks about a Gen 4 reactor system, I said, well, I know all about that kind of activity. I designed these things. I developed these material properties, these models for applications in this area. It's very similar materials, very similar temperature regimes, and that kind of thing. So that kind of experience is valuable when those programs come along that push that envelope. And it also allows you, again, the perspective to think about things that are outside the conventional. There are a lot of things beyond uranium dioxide, zircaloy, based cladding systems that have very interesting aspects, and I think in the future will have an amazing amount of application and utility, and where we're headed as an industry. Because as a couple of the panelists have mentioned, things are evolving and moving in that direction, and we're at the threshold, I think, of an era in which we're going to be applying some of these technologies in a terrestrial way, as well as, I think, moving forward as we move out into space.
Our next question is, and I think some of us already talked about this, but maybe from a more philosophical standpoint, why are you motivated to conduct space nuclear research?
I got this because it's freaking cool.
Hear, hear.
But beyond that, as nuclear engineers, we learned how to use a lot of tools for reactor design, and people have done it before and they're going to do it again. They learned it in school, and so you get to use some of these tools in a way that no one else really does. You get to design kind of concepts that may not have the same kind of, design goals as a power reactor on Earth would. So it's really fun to kind of see those tools go together and use for something that you didn't really learn it for, but it works equally well there. And really one of the big motivators now is that there's a non-trivial possibility that NASA will actually want to build an NTR to go to Mars for 2035. So I know everyone's been talking about the cyclic curve of funding. I'm going to shy away from that and say every curve is kind of a straight line if you look close enough, and right now we're going up. So there's a good chance of an NTR being built, and I want to be there like day one to apply for a job whenever Congress decides to fund it.
Yeah, I often I tell the joke that the reason I got into space nuclear power was I wanted to do science fiction without the fiction.
That's very good. I think the analogy I would use is, there are a lot of guys out there and women that work on, cars. We build 3 million, 10 million cars a year in the United States alone. So, there's a lot of really sharp, good engineers that work on those engines, that work on systems for those. But there's a difference between the guys that do that and the people who work on Formula One racers and the people who work on those vehicles and the engines and the systems that go into those. That's kind of where I look at, conventional nuclear research and development and space nuclear research. Space nuclear applications, it's the race car of our technology area. It's the high performance vehicle. It's the one that pushes the envelope. It's the one that goes beyond the conventional. And so to me, that's inherently interesting and exciting because of all those aspects, the temperatures you're looking at, the powers you're looking at, the space, the size, the applications, where you go with them. That's to me is just inherently interesting and exciting. And so it's kind of pushing the edge of the envelope, and that's always kind of a fun place to be. So to me, that's where the interest lies.
Yeah, you can summarize that with Phoebus.
Yeah.
Phoebus 2A, which was the highest power reactor ever operated. It had a power output equivalent to some very large dams in China. It was about the size of a trash can. Operated at roughly 3,000 Kelvin, so it was glowing white hot, and basically the temperature of a filament in a light bulb. Glowing white hot, they were able to pump hydrogen through it. They ran it out in the desert for 30 minutes and started and stopped it, and that's, when you really look at that, is pretty cool.
Yeah. Think about in our society, the stereotypes for people who are quite knowledgeable, right? That's not rocket science. Well, this is nuclear rocket science. That takes it up a whole different level. And that's just, for lack of a better phrase, that's just badass.
So for me, it's just because it's a necessity if we ever want to go beyond Earth orbit, that you look at the grand picture and you cannot go without nuclear power if you want to put people on Mars, if you want to put people on the moon, if you want to go beyond. So it's a path that we have to take, and we've been a little bit slow to get there, but we're going to take it sooner or later. So my passion is I want to find it when it's in the bottom of the curve, so I can be a leader when it's at the top of the curve. When people start developing it, I will have the skills and background where I can actually make an impact on the design, the development, and kind of as an engineer, we always want to leave our fingerprint on the future. We want to design something, make something, change the world, and so we can be old and say, I made that, or I did that, or I coined that term, right? So that's my thoughts.
I'm just going to echo everyone, and especially Chris at the end. I think nuclear in general, it can be very daunting to want to pursue research. There seems to be so many political, technological, so many hurdles we need to surpass. But I truly believe in doing this research. If we look at sort of like the impact NASA has on even our hospitals today, how much improvement and how much the quality of life is better, I believe that all of our research is going to eventually improve the quality of life of everyone in the future to come. And it's really a necessity for at least someone to carry on this expertise, and it is going to improve the quality of life for everyone in the future. So.
Thank you. And I guess I'll add to that. For me, why I'm motivated to conduct space nuclear research, I think that really stemmed from the community that I got involved in within the space nuclear research field, and being among other researchers that are publishing papers and doing things and staying involved, where full time is defined as a quarter of your time and 2 students, that you really start to see people there pursuing something, pursuing an ideal, and not just where the money comes from. And the chance to work with people like that every day is something that really drives me, and I want to surround myself with people like that. So the next question I have regarding funding. So how did you receive funding to conduct your space nuclear research? Did you say you were going to do space nuclear research, or what do you actually do?
Well, I have a fellowship through the Nuclear Energy University program, which has helped out a lot. And then I also had, when I applied for school, a guaranteed teaching assistantship. So if you're looking for funding, specifically in the grad school, there's really very few grants. There's not a lot of, they put out calls sometimes, but they rarely select papers or rarely select grants for funding. I've applied to many of them. So you kind of have to figure out, how can I do this, either by researching a different technology that has application for space nuclear, or if you have the backing of your school or your professors. So for example, I was saying that the space nuclear fuel has a huge relationship to safety tolerant or fault tolerant fuels and for small modular reactors. So I said in my application essay, I said, I want to work on small modular reactors and their fuel forms, but my eventual goal is I told them the truth. I said my eventual goal is space. That's where I think a lot of cool things are, and I want to use, because my dissertation is very much terrestrially focused, but the research that I can do and the time that I spend. And another way to do it is, if you're an undergrad, you can do whatever you want. If you have a senior design project, if you have, it doesn't matter if there's funding or not funding. If you have some sway in what research project you want to do or independent study class you want to do, you can, kind of find a professor that will help you. When you get into the grad school area, it's a little bit more difficult, unless you can somehow bring your own funding or find a fellowship. But you really want to keep an eye out for who's in the community and who's doing what, and make sure that you find the right advisor fit, because some advisors would not be a good fit for if you want to do space nuclear. But I was very lucky in that I found a great advisor. So.
Yeah, I would like to echo Chris again on what he mentioned for undergraduates. You have a lot of opportunities, both whether you're unfunded or not, and don't be disheartened if you apply for that dream internship and you don't get it. You still, if you build up your network, you can still be involved, whether it's unfunded. If that's not an option, there are different ways to apply. Maybe your school has a special fellowship program that they orient directly towards either mechanical engineers or aerospace engineers, nuclear engineers. That's what I did, and I worked with the different nuclear space contacts I had met, and they were more than willing to offer lots of ideas of ways I could contribute. But in terms of graduate school, I have a super supportive advisor as well. He worked on some of the development on efforts during SP 100, I think, and he sort of has a background in nuclear space, not specifically nuclear thermal propulsion, but I was able to find a supportive advisor that's really important. And I applied to NASA's Space Technologies Research Fellowship, and I was able to receive funding that way. That's really good opportunity, and it really sets you up for success. So if anyone has any questions, I could talk to you after about that as well.
So to add to those things for kind of your graduate school studies, the NEUP, which Chris mentioned, I'm going to say again, that's the only source of funding that's from the government directly for nuclear engineers. So it's you're not competing with the other sciences and things like that. This is for kind of us. So do apply to that. It's possible to get. They give about 30 or so fellowships a year. The entry pool is like 150 people, so it's pretty good. The NSTRF that Kelsa mentioned, we have another colleague that works with us at the Center for Space Nuclear Research who works kind of at there through that fellowship, so he's able to travel around. He's worked at NASA sites and he's worked for us, and he's still in grad school, so that's another great opportunity. And they do like seeing nuclear engineers apply, although you will be competing with other fields. But it seems that if you kind of look at the statistics, 1 or 2 nuclear engineers seem to get it every year, so it's really cool. And also, this is kind of maybe further out there. So if you do graduate and decide to kind of be on your own or have a kind of small business, there's the NASA SBIR, which is a Small Business Innovative Research Grant. So if you have some kind of cool ideas and some abilities, you can apply to those things, and those can turn into really large projects. So this is not really now graduate school research, but kind of just on your own side. So 3 things right there, really good to look into.
Yeah, the only thing I would add to that is, as he mentioned, and I'm glad he mentioned the SBIR program. That's an avenue once you're out of school where you have an opportunity to participate and develop some funding for a unique idea that you have. The other thing I think that's important to mention in this arena is, you kind of have to, especially outside of school, you kind of have to work with others. You have to collaborate. You have to kind of see who has like-minded interests and develop your own kind of activity based on that. And sometimes, some of us have mentioned, you kind of have to do things on the side or voluntarily. That might be the case. If you have a passion for doing that, that again keeps you kind of involved in the activities. And so you got to have to kind of cast a wide net. And as we were saying right now, there's no major commercial program out there. There's some government funding for things, but that's going to change, and it always has. If you look back at history, it will change. And so again, I think one of the key things is to keep in mind to develop the fundamental skills, the capabilities, the networking with people who are involved in it now, so that when things do ramp up again, when the opportunities do come, you'll be ready to take advantage of that opportunity.
Sometimes Wes pays me in pizza and beer.
It's not untrue.
Not untrue.
So my last question I have, which I think actually I'm just gonna more put it out to you guys, and we can address it as your questions come in. But it's any advice that our panel has for students and young professionals that are interested in space. So I asked our panel to think about that as we answer your questions. So what questions do you have for us so that we can provide you advice for space nuclear topics, for maybe even research in general, that if you have any other wild research goals or interests, maybe we can provide some experience for that.
Where do you guys see the incorporation of like private companies in space nuke? Do you see that as something that's bound to happen, or is it always going to kind of be the dividing line with specifically nuclear between government and private industry?
So I'll start with that one. That's a really good question, and because as Dr. King had mentioned earlier, a lot of the designs for space nuclear reactors, it tends to push you towards a fast spectrum. And in that case, trying to get to high power densities and trying to get to light systems that you not want to spend very much to put up in orbit, you tend to move towards designs that require high enriched uranium, which really starts to limit you if you are a private company and you're trying to, especially in today's world where we have non-proliferation risks, and where having a facility that can handle the manufacturing of materials using high enriched uranium requires a very expensive and heavy security force, and the cost associated with that is something that if you don't have literally an army to defend you, it's pretty difficult. And so I think, as Chris mentioned, one of the major barriers and the reasons why we go towards designs like that is because of very expensive launch costs. Trying to get off of the ground and getting into space is one of the most difficult things. And so if we can eliminate or at least lessen that need for such a high performance system, if we can design a system that there are certain applications that, if you can solve that Earth to Leo problem, you don't necessarily need the lightest, best performing system. Yeah, maybe for a nuclear thermal rocket you would, because you're trying to accelerate as fast as you can, or an NEP engine. But surface power, if you can get there using other means, and a chemical engine, if you could land on the moon and put your surface power reactor there, I think you could probably handle a couple extra 100 kilograms, just if that enables you as a private company to create that. So I think, and Chris can expand upon that, but I think that it's looking up for private companies, and I think it's historically, it's given that space nuclear programs have been government funded, and as Dr. King mentioned, that and Mr. Lyon mentioned that cyclical space nuclear funding, based on the period it takes to do technological development and the need for a mission that coincides with that, you sort of, I don't know, the government funding hasn't really shown to be able to follow through on that. And so I've been lucky enough to work with a group that works with students, and it seems that if funding for students is a way to get money, so that's been really nice. But then again, I work half-time on projects, so.
So the research area I'm sort of starting in right now, and I've got a student that we're working in it, and I'm hoping to expand it to something that's a little bit bigger. I'm crossing my fingers that NIEP pans out this year. Is exactly this question of we've always sort of assumed that space power, you're talking highly enriched uranium, and I think that's actually partly it's the mass constraint, but I think it's also just the standard assumption that's become we're going to have highly enriched uranium because we always have had highly enriched uranium for space power, because you look back at the original space power programs, and it was in the era when we were giving highly enriched uranium away to any country that wanted it, and because back in the 60s and 70s. We proliferated a lot of highly enriched uranium to research reactors and everything else, and it was not considered a big deal. And it wasn't until a little bit later that we started saying, hey, maybe highly enriched uranium isn't the best thing to distribute all over the world. And so I think there is in the space reactor community or the space power community a certain really strong focus or a lack of focus on proliferation. And as I get further into this, and as my experience has grown, I'm kind of the suspicion that highly enriched, we will never launch a highly. I won't go entirely out on a limb and say that, but I will say that I think it is highly unlikely that the non-proliferation people, the NNSA, will ever allow a highly enriched uranium mission to be launched for anything other than defense purposes and as a black project. I don't think you'll ever see a commercial or an open highly enriched uranium mission. And so we're looking at, if I took that constraint away, so let's look at the space reactor design concept and say, constraint number one, you can't use HEU. You can't go above 20% enrichment. How does that change everything? And suddenly we're into a totally new space of looking at things. That's kind of fun.
So there's an arbitrary limit that we've kind of set of 20%. There's no exact reason for that because it doesn't limit you from making a fast reactor. Fast reactors can easily be made with you need about 15% to make a decent one, and 20% will make a good fast reactor. So the limitations for fast reactors just because everything that's thermal needs hydrogen usually for that spectrum. And in hydrogen with high temperatures, I was telling you before that space reactors require high temperatures, there's almost no component that has hydrogen in it that can withstand these high temperatures. Hydrogen will just leave. It's very mobile. So that kind of pushes you towards a fast spectrum, but there's no reason you can't design a fast reactor. It's just you're looking at a weight penalty of maybe it's 20% heavier because you need more uranium. Your critical radius is now a little bit bigger, but it's not a showstopper by any means. And it's something that I don't see high enriched uranium being as much of an issue as just the inexperience with high temperature operation. So we have a lot of materials questions saying, will this work with this? And we've actually done a lot of that research in the past with different programs. But if you're a private company, private companies want the easiest, lowest cost, most reliable thing. They don't necessarily want the lowest mass. And that's changed from what it used to be because I was telling you the rocket industry is now cheaper. You can launch things for less money. The SpaceX rocket, their methane rocket called the Mars Colonial Transporter, is 3 times larger than the Saturn V. And it has a payload to Mars capability of about 100 metric tons. So, if you have a reactor that weighs a certain percentage of that might be okay. You don't need something really, really, really teeny, the highest performance that ever exists. So there's a trick, though, because a lot of the feedback is that nuclear in the past has been very hard to work with. It's hard to get designs approved. NuScale's going through this right now. All these reactor companies, small modular reactor companies that kind of started in the 2000s are now still trying to get approvals and things like that. So someone from an industry perspective, they say, oh, it takes too long and it's too hard. So if there's any way we can do it with another technology, we will. But the nice thing about space is that really if you look at the physics and the demands, you need nuclear. So if a private company is willing, they can do it. And their design constraints are not such that you can't do it. So it's still going to be somewhat expensive for the development, but I think like a Boeing 747 is a couple $100 million. There's a reactor right now called Kilopower that's being pushed by Los Alamos. That's a 1 kilowatt reactor that is supposed to replace RTGs perhaps someday that they're pushing. And the development on that is on par with what a 747 costs. So private industry has the money. They just don't want the risk. They want to know, will this work? If it works, for sure, they're going to put the money up.
So I think private businesses have a small role right now. There are companies like Aerojet Rocketdyne that are actively funding nuclear thermal rocket technologies, but I think the federal government will have a big role to kind of be the leader here. Kind of similar to like kind of Gen 4 technologies for reactors. You're not going to see Westinghouse making that first of a kind reactor. It's kind of on the government to kind of be that first burden. So I see the government having a bigger role in the beginning and moving, and once that's kind of out there, I think it can easily move to a small business or private business, not a small.
I think you have to look to partnerships, and as he mentioned, partnerships at the beginning with government activities, government programs, collaboration with other larger companies who have some funding that they can move in that direction. The key is to have some creativity and some drive to kind of develop those partnerships. The other thing I would look at is spin-off technology opportunities from government agencies. NASA and other government agencies routinely through STTR programs. I believe that's what they're called now.
That's correct.
Yeah, they have opportunities for spinning off technology that have been developed in the government sector that can be moved into the private sector. And so, again, it takes creativity and drive, but there may be a way to look at that. There are other companies who have interest in these areas that may not consider that technology, and again, you might pitch ideas to them to provide some low-level funding or partnership opportunities to kind of move into those areas. SpaceX is one. There are a lot of others. There's a small company in Houston, and I can't remember the name of it off the top of my head now, but it's run by Niels Chang-Diaz, a former astronaut. They're looking at nuclear thermal propulsion, Vasimir engines, all kinds of really exotic stuff. And so again, by networking and partnering and learning kind of what's out there in the landscape, you could maybe carve out a niche for an interesting idea or an application in the private sector as well.
So, any other questions? Yes.
Are there any international space nuclear efforts or communities?
So, at a small level, there are. So there's the European Union. The European Union is working on a project. They're calling it Democritos right now, but it's a multi-megawatt power source to be built to run a nuclear electric propulsion engine, so an ion engine. And it's a collaboration between France and I believe Germany and several other states in the European Union. There's also a program going on in the UK. So they're looking at developing an alternative radioisotope thermoelectric source that uses americium as its power source. So rather than plutonium-238, it's looking at americium-241. And they're looking at doing that just because of the lack of, currently we haven't really talked about it, but there is a shortage of plutonium-238, and NASA only has enough left for probably about 3 more missions. Currently, Oak Ridge is working on supplying that using the HIFER test reactor, and they're looking at supplying it at about, I believe it's a kilogram a year, or a pound, somewhere, a kilogram a year of plutonium-238, but the UK doesn't want to have to depend upon that, so they're looking at americium. I've also seen at several conferences designs put forth by South Korea at the Korea Advanced Institute for Science and Technology and at the what's the Korean research? CARI. The research, basically the National Research Lab in South Korea. We also at our Space Nuclear Conference had, in the past few years, had visitors from China to present their research that they've done. And also there's a professor in Brazil that has been doing research in the space nuclear community. So I'd say, and maybe a little bit in Canada as well. There are interests there, but not anything large, or not any large presentations I've seen recently.
Yeah, the professor in Brazil and I are actually working on the low enriched. It's on the basis of Brazil will never be allowed to make a highly enriched reactor core that looks a lot like the weapon cores we have now. I mean, when you look at the kilopower design, that highly enriched the highly enriched chunk of uranium that you need is something that only the United States or Russia could contemplate developing, because any other country developing it's going to look a lot like a dual-use device. So we're looking at low enriched so that you can go and and also commercially. That was where I was going with the whole. I sort of left that out, but so where I was going with the whole low enriched was that we're working on trying to make it so that a company, because a commercial company is going to find it a lot easier to work with low enriched uranium than they are high, and other countries as well.
That's a good point too. The work with Brazil, they're looking at applying low enriched uranium. All the presentations I've seen recently from South Korea have been space reactor designs that have used low enriched uranium. So that seems to be the way that foreign companies, not the company or group, but the other foreign countries are looking at literature training. Any other questions? We have a few more minutes, so I think 15 more minutes technically, but we can end it early if you'd like as well.
I got one.
Charlie?
You all agree that space is cool. What about the economic advantage? I mean, recouping your investment, things like that. What's the incentive to go to space?
Well, I think that's a very broad question. I think I'd answer that, and when as far as why I'm motivated to stick with space, like, is there a market for space? And I think definitely. I think with any other new land, I mean, look at the conquering of America by the Spanish conquistadors, and looking at opening up new land and new minerals and new sources, places people can live. Whenever people live in different places, they develop new issues that need to be answered through the economy and through markets. And space exploration and colonization of space will open up an unimaginable amount of new markets for people to cooperate, for companies to develop, for economies to grow. And I think any company that can nail its place in space exploration will be the first one that will have the control of the resources in that area and the property that will come along with that. So I think there's an incredible amount of economic impetus to do it, but it's risk. And one thing as humans, and one thing we see as nuclear engineers, that humans are very bad at interpreting risk, real risk from perceived risk. And one of the very high perceived risks that we as humans have is our ability to expand and do space travel, I think. So, and that's something that we as a human society have to answer for ourselves. Are we willing to accept that risk, even that perceived risk, and expand our reach out beyond just Earth orbit? So,
I mean, it's a little bit. I mean, in some ways, it's a little science fiction-y, or it's a little further out there. But I look at. I mean, the economics. The economics are still challenging. I think the joke that I heard 10 years ago still somewhat applies, which is, how do you make a small fortune in space tourism? Well, you start with a large fortune. And I think there's still some truth to that. On the other hand, I think it's important that we continue out, and I think eventually we will find things like, at some point, I think eventually someone is going to find a viable resource in space. Either we're going to find an asteroid that's mineable or something similar. I actually look at it a little more broadly, and that's that as long as we're confined to one planet, we as a species are subject to a species-level extinction event. As long as we live entirely on one shared ecosystem, we have the ability to wipe ourselves out. And that at some point in time, if we are optimistic and believe that we want to exist for a much longer period of time, eventually we have to indeed find some way to spread ourselves to different ecosystems, and to do that. And I think it's Zubrin who said that mankind will always be at risk as long as we have all our eggs in one planetary basket. But that is a ways out there. I mean, I'll admit, we have no technology that will allow us to colonize other worlds at this point in time. It is an amazing challenge to think about even getting to another solar system. I mean, we're on the cusp of discovering, of course, inhabitable planets, and if we have not already done so, on other stars. But getting there is still way beyond our capabilities. In fact, I was at a presentation where we calculated the amount of energy that it would take. The amount of energy that it would take to get a manned spacecraft to another world is, many, many times the entire energy output of the entire human species to date. And it's also a sufficiently large amount of power that we can easily wipe ourselves out upon achieving it. When we find the ability to generate the amount of power it will take to send something, unless something changes. And that's always the hope. I mean, fundamentally, if you look at propulsion technologies, there hasn't been a fundamental breakthrough in propulsion technologies in over 50 years. I mean, that, we still propel ourselves in space by shoving things out the back end. Unless that changes.
Yeah. So I'd like to paint my picture of this, in that every science fiction movie ever made, and if you look in theaters, probably about 30% are science fiction movies, is an advertisement for going to space. People want to do this, and there's billionaires who have made their money in other fields that have played, they say, I don't care, I've already made my monetary mark. I just want to go to space, retire on Mars. So what you really need is not necessarily an economy in the beginning, because the economy is, like you said, chicken and egg. It's really hard to start. What you need is a leader. You need someone who's willing to put the upfront ability. Richard Branson has kind of done that. For how much I don't like his marketing techniques, he actually has a product right now that can take tourists into space. It had a recent mess up, but that was due to pilot error, actually. But the fact is that it takes a leader who's willing to put the money up front, and when the time comes, they'll be able to commercialize it. And there's a guy named Peter Diamandis who says that space will create the first trillionaire. Because once you get to space, every country on Earth is going to be trying to race you. It'll be the space race again. The Chinese are going to want to be there. If it's a private company, the U.S. is probably going to want to try to jump in that somehow. There's going to be a huge shift towards that. So in the beginning, it's kind of like a couple space tourists who go up into a low Earth orbit for 5 minutes, or not even orbit. They just go up into a suborbital trajectory for about 5 minutes of weightlessness, and they pay $200,000 for this, which is completely high price. But in the future, the price is going to come down there, and then there's going to be a land grab. There's going to be someone finally gets to a planet, they make their stake, and then there's going to hopefully be some agreement between countries and groups over, if you build a facility here, maybe you can keep the minerals that are there. And you're not going to make money on it in the beginning, but everybody's going to be rushing out there trying to claim all these little plots of land all over the solar system, which will start the economy. And then eventually it will start producing kind of money in a way. Unfortunately, I was telling you before that the price to go into orbit is half your weight in gold, or at least it was up until about 10 years ago. And that means that even if you brought gold from an asteroid right now, it wouldn't matter, because it's still more expensive for the rocket fuel. So the economy isn't necessarily, I don't think, going to be centered around resources, but it's going to be centered around science fiction. People chasing their dreams. It's going to be like a tourism/exploration adventure. People have made their money somewhere else. They want to change it. They want to get off the planet, leave their fingerprint on history. So I say that the future of space is very bright, because you no longer need a government to achieve some of those things anymore. You can achieve them as albeit a highly funded but still private company. So I see a bright future. It could take a while. It could take 50 years. It could take 100 years. If the government really got involved and wanted to step up the ball, they could, and they could beat out the private industry. But it seems like no one's in the government. It hasn't, it would take the reanimated corpse of JFK to really push us into space right now. We have no strong direction. Everybody's still talking about, where do we want to go? Do we want to go to the moon, or to Mars, or to the asteroids? But in the private industry, we do have leaders. We have people that maybe won't make the best decisions, but they're going to stay the course and follow through. So that's what I see, is that the real key benefit of private development is that you have a leader, someone who can say, we're doing this, and we're not going to argue about it, and if I spend all my money, then we go bankrupt. Oh well. So leadership.
Yeah, I think you have guys out there like Elon Musk at SpaceX who, if somebody was said, hey, I'm going to develop a new space company from the ground up in the next 10 years, I'm going to drop the price. I mean, what he's been able to do there is something I would not have believed could be done, and yet he went out and did it. There's that corporation out there, Planetary Resources. They're planning to go to asteroids and mine them and bring materials back. They're investing all kinds of money, and I think the key is entrepreneurship and leadership in the private sector that says, look, we're visionary, we have a lot of money, we're going to use it in this direction to develop technologies and opportunities. And I think there are other private companies that can ride the coattails of those activities, if you can find a way to work your way into that position, that there will be economic benefit. Up front, these people are investing millions and millions of dollars up front for a future they believe is going to pay them back. They're not doing it just for fun, but they're doing it because they think they can achieve something and they have the means to achieve something. Other companies can partner with them, develop technology for them, and that pays the way right now. I mean, if you got a contract with Planetary Resources to develop a piece of technology, you're funding what you're doing, right? You're getting something for that. If you have an idea that SpaceX needs a piece of technology and you can convince them to pay for it, you've got an economic incentive to develop that technology, to be part of that. And so I think, again, there's an element of risk, just like there is in any business venture. But there are opportunities there, both in the government to a lesser degree and in the private sector now to a growing degree. I mean, Virgin Galactic, SpaceX, Planetary Resources, those companies didn't exist 10 years ago. But now they're spending millions of dollars in developing space technology. And so that trajectory of that activity is pointing up. And so it's an interesting time. Uncertain, but very interesting time.
So all of us panel members will be around the conference today, and we'll be available to talk with you to answer any of the questions that you may have if you have interest about fellowships, scholarships, programs as a student. You know, all of us were students at one point, so we have that experience and can talk with you just one-on-one. I'll be standing at the INL booth if you want to come by and learn more about INL, about CSNR. To put a plug in for our Aerospace Nuclear Science Division, our group, our community of space nuclear people, I want all of you to pull out your phones right now and open up Facebook and join our group if you're interested in joining our space nuclear community, because all of us here are members, I think, except Bill and I.
Except me, and I'm about
Bill's
to join.
About to join. So like we all post stuff. We post information about these scholarships, fellowships. Actual scientists that do this research are on this Facebook group. You're gonna search ANSTD on Facebook, and that's the Aerospace Nuclear Science and Technology Division. And join that group. Me or Chris will approve you, and you can communicate and join in on that community. So I think this concludes our panel today. Thank you very much for attending, and it was a great panel.
Very informative.
So, real quick, everyone, I don't know if everyone has the app or not, but the student section committee meeting is in this room starting at 11 today as well. So if you're planning on attending that meeting, you don't have to go far. But lunch is already provided, so if you're planning on coming back for that, go ahead and grab lunch for that. All right.
Nice to meet you.
Yeah, nice to meet you. Yeah.